Hey guys, Julie here. Welcome back to Hardware 3D. Today, we're looking at shadow bias. So, lots of explanations, probably some chilly diagrams going to be coming at you. Just a little warning there. But first off, let's just take a look at what we got so far. In the last video, we had this. And I think you'll agree it's a little funky. But why? Why the funkiness? Well, here's the thing. So, with shadow mapping, you've got your light source. You're going to render from the perspective of the light source. You're going to build up this depth map. That's your shadow map. Then, when you render from your camera's point of view, for every one of these points in here, you're going to figure out, well, how deep is that from the perspective of the light? This point that we're looking at. And then we're going to compare that to the depth recorded in this texture here. And that comparison lets us know whether or not the thing is shadowed or not, right? That's the basics. That was covered in a previous video. If you don't understand that, then you really need to freaking go back to that video. But anyways, now here's the problem. These are floating point numbers. They're subject to, error, uncertainty, because they have limited precision. Now, what we're essentially doing here is we're trying to compare two values that are identical. Only those values are calculated through different pathways. The value that is written into this depth buffer is calculated by, doing the normal pipeline rendering and then storing the depth. The depth that's calculated from the point of view of the camera is calculated by, doing different interpolations and applying the same transform here. But the steps aren't going to be all exactly the same. So when you're using floating point numbers and you're doing two different calculation pipelines, mathematically, if you look at the equations, they should be equal. But if the steps aren't performed exactly the same, your end results are going to be slightly different. And so what is going to happen is that, perhaps this thing, they should compare equal, but it turns out that the value in the depth buffer is a little closer than the value that we calculate here. And so that would make it appear as though it were shadowed. So what we actually have to do is when we're calculating here, or we could do it in the depth buffer, we could do it either way, but at one of these points here, we have to add a little error value, a little epsilon, and we call that the shadow bias. And by adding that error, what it's going to do, well, let's say we subtract the error, the depth, from the value calculated from the camera position. That will bring that value just a little bit in front of the value recorded in the depth here. Not too much, not enough so that it will, mess up comparisons with other objects, but enough so that the surface itself won't get messed up by small discrepancies in your floating point calculation. Now, before we jump into the code for that fix there, just a small little note here. When Visual Studio was upgraded to version 16.6, it broke some stuff, or it broke one thing in the code base of the engine that has to be fixed. So people have been reporting this. It's a very easy fix. In pass.h, all you got to do is add memory. So I've just spliced that patch right into here in the beginning of this history after the fact. But if you are trying to check out earlier things and you're getting build errors, maybe you want to try to add this include into pass.h. Just a small little thing. But yeah, so fixing that shadowing, not a big deal. All we're going to do is we're going to subtract a little bit from the depth that is calculated during the main rendering pass. Just subtract just a teensy little bit here, and that'll make all the calculations go nice. This comparison here, this should really be a greater than or equals, right? Because in a perfect world, if you were to do your calculations and there were no floating point error, these two values should actually be equal when the thing is lit. They should be equal. So this should be a greater than or equal to comparison. But with the way that floating point error works and the fact that we're adding a bias, actually greater than by itself just works fine. The important thing here is that you have to have this bias. If you just do greater than or equal without the bias, it ain't gonna work. All right, so here we are with the bias in there. And now the face is perfectly lit. Very nice. This one here is in shadow. If I move our light here, now we're getting the shadowing on this side. And yeah, we can see it now. This part of the second cube is being lit. Everything looks like it's working properly. Now, this next thing here, this next commit is a little bit of a goose chase that I sent myself on. And I'm not going to spend all the time it would take to explain the goose chase to you. But basically, I thought to myself, well, I mean, we were doing the perspective divide here in the pixel shader. So we're doing a division per pixel. Division is a relatively expensive operation. What if we could push that up onto the vertex level? And I thought to myself, well, why can't we? There's reasons why I thought that. Basically, the fact that depth is already divided by Z, so interpolating it in the screen space, I figured we might be able to swing it. And for a bunch of different reasons, that doesn't work. But what happened was I tried it out, and for our very simple test scene of those two cubes, it seemed to work properly. So here we are with the Z divide in the vertex shader, and you know what, I move this, it looks, the results, they look okay for this very trivial test that is actually not a very good test at all. And I looked at this and I said, I'm a genius. I've done this amazing optimization, pat myself on the back, and commit that stuff. And then later on, I figured out, you can't, life ain't that easy. But anyways, let's just move on from now. So now that I ostensibly have this working with my simple test of only the cubes, I want to bring the shading goodness to all the things in my scene. And that means I've got to rework all the shaders to, incorporate those dynamic shadowing steps, shadow mapping. And, I don't want to copy and paste that code into every one of these shaders. I'd like to factor out all the shadow stuff into its own HLSL include file, and then include that in all of the, in all these things here. So to do that, first a little refactoring, because before I was naming these files as .HLSL, the includes, I was naming them as HLSL, but that's not good, because if you name a file as .HLSL, the Visual Studio is going to try to compile it. So you've got to manually disable compilation. That's annoying, right? But there's actually an extension for that. It's called HLSLI, and that signifies it's an HLSL file. The code completion and the syntax highlighting will still work, but the compiler won't try to compile it by default. So I rename all the includes to HLSLI, and that means that I've got to change all these include statements to reflect the new names. But that's basically all. The thing I did here was I deleted some files that weren't being used anymore, just some detritus. I got rid of it. And what else? This is a thing. For all of our constant buffers going forward, eventually we're going to want to manually specify the register for them, because not specifying it causes a problem where now the order depends on how things are included, and just that sort of thing is going to cause us issues. So it's better to manually specify that, okay, the transform is going to be in, constant buffer 0 register 0, or slot 0 if you like. So those are the main things, just HLSLI, deleting some stuff, and specifying register. Just a little bit of refactoring. Then I create the include for the vertex shader stuff. So for shadow mapping now, we have the transform, and that will be always register or slot 1 of our constant buffers. And then just all the converting a vector to the screen space with respect to the light, which I call the shadow screen space. And yeah, this is just the stuff that was in this vertex shader here. We pull it out of shadow test, we put it in its own include, and we include that into shadow test to make sure everything works. So we do that for the vertex shader, then we also do it for the pixel shader. So create a little function here, it returns a bool telling whether or not the thing that we're looking at is occluded. And it's the same stuff that we had in the pixel shader, and we're also going to put the required shadow map texture and the sampler, and we're going to give them, explicit slots to bind to. So then we can pull that stuff out of the pixel shader here, and we just do if shadow unincluded, unoccluded, then we do our lighting calculations for that fragment or pixel or whatever you want to call it. So now we have these includes and they're working in the shadow test shaders. The next step is to include them into all of our other shaders, and that way we can see shadows cast on everything in our scene. So in this commit here, we are including into our other shaders. And if we look at the name of the commit, things obviously didn't work out as we would have liked. But let's see how this stuff is included. For the vertex shaders, it's basically the same story for each one of these. You're going to add something called shadow cam screen, and you're going to call the function to shadow screen space. And you're going to include the V shadow. That's it. You do that for each one of these. It is all the same story. By the way, just a side note here, this nose perspective thing, what this is saying is when you interpolate these outputs from the vertex shader, don't perform perspective correction on this attribute. And that was basically necessary for my idea in my head of being able to do the perspective divide in the vertex shader. But it turns out that that's not actually possible. We'll see that in a little bit. But this nose perspective, it might come in handy someday, especially if you wanted to create a game that replicates that, PS1 era aesthetic of very bad textures and, with those weird artifacts. And this would be one way of achieving that. So if you ever want to create a PS1 stylized game, this might come in handy for you. Otherwise, probably not going to be that useful. But yeah, that stuff aside, let's look at the pixel shader. Pixel shader, going to include pshadow.hlsli. For these object buffers, we're now giving them an explicit register, explicit slot that they all bind to. So these object cbuff will bind to slot 1. Slot 0 is, of course, the slot that is reserved for our lighting information. Then down here, we are going to make our shader here take in the shadow position. And it's going to do this test here to see if the shadow is occluded or not. And if it is unoccluded, then we execute the normal shading. Now what we're doing here is we're setting up these variables, diffuse and specular. And then if we have unoccluded and we're doing our lighting, we set those as normal, our normal calculations. But if we are occluded, if we are in the shade, so to speak, then we want to set our diffuse and specular to 0. We're not getting any diffuse and specular. The only light that's hitting it is the ambient light. There's no direct lighting from the light source because it is occluded, obviously. And then you just add those together here as usual. And it's the same story for these other guys here. Explicitly setting the register slot, including pshadow, changing the shader function signature, and executing our shadow test. Same story for diffuse, normal, diffuse, specular. Seems to be the same story. So with that stuff all set up, should be working, right? All of our things now should be able to receive shadows. They won't actually be casting. The only things being casting shadows are the cubes. We'd have to set up the techniques for shadow casting in the other objects, the other models in our scene. But they should be able to receive. So now with those shaders all set up, we should be able to see shadows being cast on everything in our scene. The only things casting the shadows should still be only the cubes because of the way we set up the techniques. But everything else in the scene should be able to receive shadows. And here's what we have. And let me tell you, doesn't quite seem right, does it? There seems to be various problems here. I mean, the shadows being cast onto the curtain here, they seem actually pretty good. This seems to be working. But this floor here is pretty messed up, right? And everything behind the light is also messed up. So we've got various problems here that need to be addressed. Now, the first thing I do when I got problems is I probably want to run it in debug mode. And often I want to attach the shader debugger. Now, when we run in debug configuration, we immediately get an exception thrown. So that's a problem, right? It's going to kind of put a monkey wrench into our plans of debugging our program. Now, I have my debugger here set to, here we see exception settings. So basically break on all exceptions not in this list, which includes, our custom exceptions. But I want to see the exception message. We built in our framework very nice, message box that displays a bunch of information about what's gone wrong. So instead of having to try to dig through it in the debugger here, I just like to have it presented to me in my message box. And you can do that. If you break on a thrown exception and you want that to propagate out, you just got to go continue. Now here, something bad happens. Debug error, abort has been called. So it did not propagate. It did not give us our nice message box. It just killed the program. And this is actually indicates that some of my code here for the way exceptions are handled is not correct. And we can solve this problem. It's not that hard if you know what you're doing. So we'll run it again. We'll get that exception. So there's something that is preventing the exception from propagating up to our reporting code. How do we see how that works? Well, we look in the stack, call stack. We see what is calling this. Well, bind buffer graphics resources. This exception specifier is no except when not in debug, but we are in debug. So this should allow exceptions to propagate. What's the next one? Bind all. Here's the culprit. Bind all has been marked as no except, so it'll never propagate exceptions, except we want it to. In debug mode, we want it to propagate exceptions. So, fixing the problem, no except not debug, and we gotta do that and we gotta do the same in the header file here, no except not debug. And if we build this now, again, we get the exception. It breaks on the exception, but if we press continue, we should get our message box. And here we can see the thing that caused Direct3D to give us some guff. And the thing it says here, resource being set on output merger, depth stencil, is still bound on input, forcing pixel shader resource slot 3 to null. So basically, the reason for this issue, and this happens to me a few times as soon as when we started getting into the multipass rendering, where we're rendering two textures and then we're binding those textures as inputs to other stages. What happens is we render and we bind a depth stencil. All right, that's step one. Then when we're rendering our main scene, we bind that depth stencil, that's the shadow map, we bind that as an input, as a texture input to the pixel shader. And that's fine, that works. Then we go to the next frame. We try to bind that same resource as a depth stencil output, but it's still bound as an input to the pixel shader. And the debug runtime of Direct3D says, hey, you're trying to bind something as an input and an output. That's not cool. I'm going to throw a warning. It still works in release, and it works in debug as well. In what it does is it just forces that's thought 3, that input to be null. So it unbinds it as an input when you bind it as an output. But it throws this warning, and since our code is, built to stop and throw an exception on these warnings, our program can continue in debug mode. So there's two ways to handle this. One way is disable this specific warning. You can disable in DXGI debug info, you can disable specific warnings, and then it won't report this issue to us anymore. It will just silently unbind it from the input. And that's very easy, but that's the coward's way out, because we don't want to disable warnings if we don't have to. Disabling warnings means that it can't report issues to us. Maybe in the future, there will be an issue where we're trying to bind something as an input and an output, and we're making a mistake and we're not realizing it. It would be nice if the debug runtime could inform us of that mistake. But if we silence warnings like these, that will prevent us from giving us good information in the future. So the other option is to somehow find a way of unbinding things that have to be bound to as both an input and an output at different passes, unbinding them when they're not needed anymore. And there's a bunch of ways we could go about it. I took a fairly simple route. What I did was in graphics.cpp, when we begin frame, we're just going to unbind some of these textures that are used as inputs and outputs. So slot 0 is often used as a full screen input for things like our blur filtering passes. So I unbind that at the beginning of a frame, and I also unbind slot 3, which is used as our shadow mapping texture. So we start each frame with a clean slate, and then these problems of bound textures being carried over between frames doesn't cause us issues anymore. This one here, I just added a small comment, doesn't matter. So we fixed that issue. Now we're not getting the issue with the debug. That allowed me to run my program in debug mode, look at it, and I found one issue, one pretty big issue, and that issue has to do with our shadow mapping. Basically, imagine, okay, we're rendering our scene from the point of view of the light. That has a frustum, has a transform, and it's got a near plane and a far plane. And so let's say the far plane is here. Now we render from the point of view of the camera. Now the far plane of the point of view of the camera might be farther than the farthest point from the point of view of the light. And what happens then? Well, let's say we're rendering a point here, and now we transform that into the space of the light. What's the Z going to be? Well, it's going to be Z that is greater than 1. That's a problem. That's a problem because now that is outside of the acceptable range of Z values. Z should be between 0 and 1. We now have Zs that are greater than 1. And when we try to do our depth comparison on those, it is going to fail automatically. So we have to do a little special case, especially in our situation here, where our shadow map rendering is only being used for a small portion of the scene. It can't capture the entire scene. So we've got to do a special case for what happens when we're trying to render stuff that is outside of the range of the shadow map. And the way I handle that is we're just going to do a little test here. Is the shadow screen position, is it greater than 1? If the Z is greater than 1, then we should just automatically say that this point is unoccluded. It was outside of the range of rendering our shadow map, so our shadow map has nothing to say about this point. So let's just let it pass the test. All right, and when we do that, we notice, okay, right away, now stuff behind the light is working correctly. And, well, I mean, it's looking still kind of messed up over here, right? So we still got problems. I mean, this is obviously a problem. So we're not shadowing everything, but I mean, the projection of the shadow map here is definitely funky. We must admit this is a funky projection, which is funny. The projection looks fine on the curtain here, but on the floor, it's all kinds of messed up. Now, one thing that you're going to note here is with respect to the light and the camera that we're using at the light's point of view to capture the shadow map, this stuff here has pretty much a constant Z value. Z doesn't change. However, the floor, we see the Z value is receding, right, away from the camera. So this kind of gives us a hint that the problem with our shadow projection is somehow a problem with Z. And if you were paying attention, you know that I did some crazy bullshit having to do with, trying to do the depth divide in the vertex shader instead of in the pixel shader, which also obviously affects Z. So with that clue in my belt there, I realized, okay, perspective divide is not working in the vertex shader. So I changed the vertex shader to not do the perspective divide here. We go back to what we were doing before, which is we pass in the undivided. We pre-multiply the W by this offset here, because it'll get divided out again, and then it will get the correct value in the pixel shader. And because we're passing out the undivided value, now we got to output a float 4 instead of a float 3. We're outputting in homogeneous coordinates, basically. Then in the pixel function here, we're going to take in a float 4. We are going to divide XYZ by W, and then we're going to, do the same stuff that we were doing before. Now, because we've changed from a float 3 to a float 4, that means now all these functions got to change in just one aspect. We got to change this from a float 3 to a float 4. So that's what's changing in all these bad boys here. In the vertex shader here also, we have got to now remove that no perspective. We have to perspectively correctly interpolate this homogeneous position, and we rename it from shadow cam screen to shadow homopause. And that's it. So that should fix it now. We're doing our perspective divide in the pixel shader per pixel. And now we see, yeah, shadows look like they be where they're supposed to be. Yeah, that looks correct, right? If I put the shadow camera, if I point it in a slightly different direction, and then let's see if I can move my cube. It's times like these where it's really nice to have like some kind of widgets to manipulate this stuff, but maybe one day. Maybe one day, yeah. So now we can see all the stuff in the scene seems to be correctly receiving the shadows that are cast by our cubes. So obviously now, next step is to get all the things in our scene to cast the shadows. And that part isn't actually that complicated. The only things in our scene that need to cast shadows, besides the test cubes, are all the things that are loaded as, object models using asimp. And all those things, their techniques, they're all controlled by material, right? So material.cpp, all we're going to do, and I commented out that code. So it's kind of just uncommenting code that I had before for the most part. Just adding the technique for shadow mapping. And when we add this technique to all of those drawables of our model node mesh system, then all those meshes, they'll be drawn and they'll render themselves to the shadow map and everything will be fine. So there's just one change, allows everything now to render to the shadow map, which means all the information will be in the shadow map when we render the objects in our main pass. So here it is in all of its glory. We should have full shadowing enabled here. Let's look at our camera for our light. And we do this, and yes! Now, I keep forgetting his name, Nanosuit. The Nanosuit is casting shadows on the wall here, behind it. And it's a beautiful thing. It's a beautiful thing to behold. Now let me show you one little issue here. And this will tie into next video, because I think I'm about ready to wrap this one up. So I'm going to point the camera down a lot. And we're going to look at the feet shadow here. Look at this. Does this not look strange to you? This foot is the foot is directly on the ground. But this shadow here, it's kind of a little off, ain't it? Don't it seem a little off? Like the shadow should be starting around here and coming out. But it's like it's offset from the foot a little bit here. And that is going to tie into our next video, which I'll give you a little bit of information here. It's this artifact here is called Peter Panning, is what people tend to call it. And it's caused by our bias. So our bias does good work for us, but it also causes new problems. And that's a theme in shadow mapping. You have problems. You got 99 problems. And you do some stuff that creates a solution for you. Only it also creates new problems. Next video, we're definitely going to be continuing on with shadow biasing. We're going to look at this problem here. We might also start to look at this problem here, which is also annoying. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more Hardware 3D.